In this lesson, we're going to be talking about the term moles, which is a unit of measurement that we use in chemistry to quantify the amount of a substance that we have. And what we tend to be talking about are atoms and molecules. We are talking about incredibly small particles, which means there's a very, very large number of them. So when we say amount in chemistry, it can mean one of two things really. It can be mass. If I was to ask somebody to pass me an amount of magnesium, I might specify I would like 10 grams of magnesium. So we use mass for amount, but that doesn't work when we're talking about number of particles, number of atoms, because if we look at this example here, 10 grams of calcium and 10 grams of magnesium, that isn't the same number of atoms. Because we know that calcium, if we look at the periodic table, every atom of calcium has a relative mass of 40, whereas magnesium has a relative mass of 24. So they both weigh 10 grams, yet each individual atom of calcium is heavier. So if they both weigh 10 grams, I'm going to need almost twice as many atoms of magnesium to make up that same mass. It's very similar to that riddle, what weighs more, a ton of bricks or a ton of feathers? Well, they both weigh a ton, but which one would you have more of? Well, obviously you would need far more feathers to make up a ton than you would bricks, because the bricks individually have a greater mass. So it's the same here. When we're talking about atoms, when we're talking about molecules, the relative mass of those atoms and the relative mass of those molecules is really important. So when we are looking at how atoms interact and how molecules interact in chemical reactions, it's very difficult for us to talk about in terms of mass. Actually, what we want to talk about is moles, because if I had 10 grams of calcium and 10 grams of magnesium, I would have a very different number of atoms. So we talk about moles rather than mass. So quickly, which one of these contains the most atoms? It's going to be the magnesium, because magnesium atoms have a lower relative mass. Therefore, more are needed to make 10 grams than of calcium, which has a higher relative mass. So the concept of a mole is not that dissimilar to the concept of a dozen. Okay, so this is a term that you will almost exclusively only come across in chemistry. Okay, so there's a lot of crossover in a lot of the stuff we do and a lot of the terms we use in maths and physics and biology and other subjects. But moles, outside of talking about small rodents that live underground, moles is a term of measurement that is almost exclusively used in chemistry. Now, we'll come back to moles, but I just want to talk about a dozen first. Now, hopefully everybody is aware that a dozen means 12. So if I told you I had a dozen eggs, you would know I was saying that I had 12 eggs. If I said I had half a dozen eggs, you would know that that would be half of 12, which would be 6. If I said I had 2 dozen, you would know that that's 2 times 12, and that would therefore be 24. Now, when you're talking in dozens, you don't have to talk about eggs, you don't have to talk about bread rolls or bakery goods. You could talk about anything. You could have a dozen chairs, you could have a dozen students, you could have a dozen atoms. It's just a term that we know means 12. And moles is a very similar term in that it means a particular number. Now, because we are talking about atoms, because we're talking about molecules that are incredibly small, we are talking about very, very, very large numbers. In in 10 grams of calcium, we're looking at billions of atoms. Just in the smallest measurements, we are talking about billions and billions and billions of atoms, billions and billions and billions of molecules. So we need a really big number, and that's where this number comes in. It's called Avogadro's constant, and it is equal to 6 times 10 to the 23. Now, sometimes you might see that a little bit more. You might see it to 3 significant figures as 6.02 times 10 to the 23. But essentially 6 times 10 to the 23. Now that is how many 1 mole is. So if I had 1 mole of anything, let's say I had 1 mole of eggs, I would have 6 times 10 to the 23 eggs. If I had half a mole of eggs, I would have half that number. I'd have 3 times 10 to the 23. So it works in the exact same way as a dozen. You just need to know that 1 mole is equal to 6 times 10 to the 23. So if in a question you are told that there are 2 moles of magnesium, well then you know that that means there are 1.2 times 10 to the 24 atoms of magnesium. That's precisely what that information is telling you. And it's much easier to say I've got 2 moles of magnesium, or I need 2 moles of magnesium, than it is to say I have 1.2 times 10 to the 24 atoms. It's just a simplification. So you need to know that it's called Avogadro's constant. You need to know that it's equal to 6 times 10 to the 23. And you just need to know that that is what 1 mole refers to. So if you had half a mole, you would half that number. If you had 2 moles, you would double that number. If you had 10 moles, you would multiply that number by 10. So let's have a look at these questions then. So if I had a dozen atoms, I would have 12 atoms. If I had 2 dozen molecules, that would be, a dozen is 12, 2 12s are 24, so I'd have 24 molecules. If I had half a dozen eggs, well 1 dozen is 12, half of that is 6, so I would have 6 eggs. Now I've got 1 mole of staples, so that would mean I would have 6 times 10 to the 23 staples. If I had 2 moles of sodium atoms, well if I've got 2 moles, that's 2 lots of 6 times 10 to the 23, which is 1.2 times 10 to the 24 sodium atoms. If I had half a mole of water molecules, well half of 6 times 10 to the 23 is 3 times 10 to the 23 water molecules. Now this question, my coffee contains 17 moles of water. How many molecules of water are there? Now I can't do that one in my head, but all you've got to do is the 17 times Avogadro's constant, so 17 times 6 times 10 to the 23, giving us our answer 1.02 times 10 to the 25. And that is actually not far off being the truth. If I had a cup of coffee, it would have roughly that number of water molecules present in that 1 cup. So again, huge numbers because we're talking about very, very, very small particles. So if we consider a slight variation on the diagram we saw before, this time I've got 2 blocks, one of calcium, one of magnesium. This time I've not quantified it as mass, I've quantified it in moles. So I've got 1 mole of calcium, 1 mole of magnesium. Which block contains the most atoms? Well, they are the same. They contain the same number. Because they're both 1 mole. And we know 1 mole is equal to 6 times 10 to the 23 atoms. Therefore, same number of atoms of each element. So I would have 6 times 10 to the 23 atoms of magnesium in this block. I would have 6 times 10 to the 23 atoms of calcium in this block. Now, really, I should have drawn this block being slightly smaller than this block, because obviously the magnesium atoms are smaller and lighter. So if I were to weigh both of these blocks, if I had 1 mole of calcium and 1 mole of magnesium, then the calcium would weigh more because I've got the same number of atoms, but each individual atom in calcium is heavier than the individual atoms of magnesium, because if we just remind ourselves, the calcium atoms have a relative mass of 40, whereas the magnesium atoms have a relative mass of 24. So if I had the same number of atoms of both, then this block would be smaller and way less than this block. This block would be larger and way more because the atoms are larger and heavier. So this square here probably should be smaller. So this all brings us back to, we now know what a mole is. It brings us back to balanced equations. Now, balanced equations, up until this point, you've written them because you've been asked to. You've been told to write a balanced symbol equation, and you've been told how to do it. You're trying to get the same number of atoms of each element on the left-hand side of the reaction as there are on the right-hand side of the reaction. And the justification for that is conservation of mass. Elements aren't created or destroyed in a chemical reaction, they're simply rearranged into new substances. So you're not going to create atoms of an element and you're not going to destroy atoms of an element, they're just simply going to be rearranged. So there must be the same number of each on both sides of the reaction. So that's how you've been balancing them, and that's been the justification for balancing them. But actually a balanced symbol equation fundamentally tells you the ratio that these substances combine. It tells you the ratio in which the reactants combine and the ratio in which they produce their products. So these numbers, these what we call coefficients, these large numbers that go in front, so here we've got 2, there's no number here which means it's 1, and then there's another 2 here, that gives us the ratio, and it gives us the ratio of moles, not of mass, the ratio of moles. So a mistake people make is they think, well, if I had 2 grams of magnesium, it would react with 1 gram of oxygen and give me 2 grams of magnesium oxide. And that's not true, because all of these atoms and all of these substances have different relative masses. So you can't use the ratio to compare mass. What you can use the ratio to compare is moles, because moles have the same value. 1 mole of a substance is always 6 times 10 to the 23. So you can compare the ratio of moles. So what this is telling us is that for every 2 moles of magnesium I need 1 mole of oxygen, and it will produce 2 moles of magnesium oxide. Now, this is a ratio, so it doesn't mean that you have exactly 2 moles of magnesium and you need exactly 1 mole of oxygen. If you had half a mole of magnesium, then you would just need to look at the ratio to work out how much oxygen you would need. So if I had half a mole, 0.5 moles of magnesium, well, the ratio is 2 to 1. So what's half of 0.5? Well, 0.25. So if I had 0.5 of magnesium, I would need 0.25 of oxygen, and it would produce 0.5 of magnesium oxide. It's just maintaining the ratio. So these values just tell you the ratio of moles, not the actual values of the moles. So, how many moles of magnesium oxide would be produced from 4 moles of magnesium? So the ratio between the magnesium, so they've asked us to say how many moles of magnesium oxide are produced from 4 moles of magnesium. So what is the ratio between the magnesium and the magnesium oxide? It's 2 to 2, which if we simplify that is 1 to 1, which means however many moles of magnesium I have, I'm going to get the same number of moles of magnesium oxide produced. So if I had 4 of magnesium, I would get 4 moles of magnesium oxide. How many moles of oxygen would be needed to react with 6 moles of magnesium? So if I had 6 moles of magnesium, the ratio between the magnesium and the oxygen is 2 to 1, meaning however much magnesium I have, I need half as much oxygen. So if I had 6 moles of magnesium, I would only need 3 moles of oxygen in order to react with it. How many moles of magnesium would be needed to form 3 moles of magnesium oxide? So if I wanted 3 moles of magnesium oxide to be produced, how many moles of magnesium would I need? The ratio is 2 to 2, which we've just said was the same as 1 to 1. So if I wanted 3 moles of magnesium oxide, I would need to use 3 moles of magnesium. and how many moles of oxygen would be needed to form 0.5 moles of magnesium oxide. So I want 0.5 moles of magnesium oxide to be produced. The ratio is 2 to 1, so I need half as many moles of oxygen in order to make that happen. So if this is 0.5, then this must be 0.25. Now here we have a different reaction, but it's the same principle. We look at the coefficients, we look at the large numbers in front of our substances. So we've got a 2, another 2, another 2, and then there's nothing here, which means it's a 1. So the ratio is 2 to 2 to 2 to 1. So for every 2 moles of lithium, I need 2 moles of water. It will produce 2 moles of lithium hydroxide and only 1 mole of hydrogen. So, how many moles of lithium would be needed to form 1 mole of hydrogen? So if I wanted 1 mole of hydrogen, how many moles of lithium would I need? Well, the ratio is 1 to 2, so I would need twice as much, so I would need 2 moles of lithium. And how many moles of lithium hydroxide would be produced if 2 moles of H2 are produced? So if I had 2 moles of hydrogen produced, I would get twice as much lithium hydroxide produced because the ratio is 1 to 2. So twice as much of 2 moles is 4 moles. So I would get 4 moles of lithium hydroxide produced. Now when it comes to the actual reaction itself, it's very rare that you have the exact right number of moles of all of your reactants. If we were looking at those ratios before, it's very unlikely, especially the ones that involved oxygen in the air. Well, you can't really control the abundance of oxygen in the air. You probably got more oxygen than you need. So if you were reacting, let's say we had some magnesium that we were heating up in a Bunsen flame, would that use up all the oxygen in the room? No, of course it wouldn't. There would be loads of oxygen left. So it's in excess. There was more oxygen than was needed. So when we are looking at chemical reactions, most of the time you have one reactant that runs out and the others, there will be some left over. So the reactant that runs out is what we call the limiting reactant. So that is the reactant that has the fewest number of moles, and because it runs out, all of those moles of that reactant get used up, the reaction stops, which means that the other reactants, where there are some moles of that reactant left over that haven't been used, we call that excess. So we have limiting reactants and excess reactants. So we can use the equations to identify which reagent is in excess or which reagent is limiting. So we're going to use this equation here. So 2 moles of sodium hydroxide are added to 2 moles of sulfuric acid in a neutralization reaction. So the easiest thing to do here is to annotate one of your reactants. So we've got sodium hydroxide, we've got sulfuric acid. It doesn't matter which one you go for, but you annotate one of them. So I'm going to go for the sodium hydroxide. So I'm going to say 2 moles of sodium hydroxide. Now, the ratio with the sulfuric acid is 2 to 1. If we just annotate the ratio, so we're looking at 2, there's nothing in front of this, so that means it must be 1. There's nothing in front of this, which means it must be 1. And there's nothing in front of the water, which again means it must be 1. So the ratio is 2 to 1 to 1 to 1. So if I had 2 moles of sodium hydroxide, I would only need 1 mole of sulfuric acid. As it turns out, I've got 2. So I've got more than I need. I've got twice as much as I need. So this reaction is going to run out when the sodium hydroxide runs out, because I've got the exact number of moles I need of sodium hydroxide, but I've got twice as much sulfuric acid as I need. So there's going to be 1 mole of sulfuric acid left over at the end. So which reactant is in excess? It is the sulfuric acid. Which reactant is limiting? It is the sodium hydroxide. and the explanation being there are twice as many moles of sulfuric acid as are needed. It only needed 1 mole, but we had 2. Let's look at the next one. So here, 0.5 moles of aluminium is added to 1 mole of sulfuric acid in the following reaction. We need to identify what is in excess and what is limiting. So again, we'll look at the ratio first. So the ratio is 2 to 3 to 1, because there's nothing in front of it, so it's 1 to 3. So the ratio is 2 to 3 to 1 to 3. So for every 2 atoms of aluminium, or 2 moles of aluminium, you need 3 moles of sulfuric acid. It will produce 1 mole of aluminium sulfate and 3 moles of hydrogen gas. So again, we've got 2 values here. We've got 0.5 moles of aluminium or 1 mole of sulfuric acid. It doesn't matter which one you start with, but again, I'm going to start with the 0.5 moles of aluminium. So if I had 0.5 moles of aluminium, how much sulfuric acid would I need? So the ratio is 2 to 3. Now this one is slightly more complex because you can't necessarily do a straight comparison, but it's simple as if the ratio is 2 to 3, well, if I do 0.5 divided by 2 times by 3, I would need 0.75 moles of sulfuric acid. Well, how much do I really have? Well, I've got 1, haven't I? So I needed 0.75, but I've got 1. So I've got more than I needed. So the reactant in excess, again, is the sulfuric acid. The limiting reactant is the aluminium because it has the fewest number of moles. It will run out first. So my explanation is there is 0.25 more moles of sulfuric acid than are needed to react with 0.5 moles of aluminium. Now finally, there are 3 questions for you to have a go at doing the same thing. Identify the ratio first, the ratio of moles, and then use that to work out which one of these is in excess and which one is limiting. And then finally, there are a couple of other questions using that limiting reactant, and that's what's important, because the limiting reactant determines how many moles of product are formed. Okay, so if we just do this first one quickly, so 1 mole of gallium is added to 1 mole of copper sulfate. So the ratio is 2 to 3. There's no number there, so it must be 1 to 3. So 2, 3, 1, 3. That's your ratio, okay? So we need to work out which one is in excess first. So we've got 1 mole of gallium reacting with 1 mole of copper sulfate. So the ratio again is 2 to 3. So if I had 1 mole, so if I do 1 divided by 2 times by 3, I would need 1.5 moles of copper sulfate. I don't have that. I've only got 1 mole. So this is my limiting reactant. Okay? So the excess reactant this time is the gallium. My limiting reactant is the copper sulfate, because if I had 1 mole of gallium, I would need 1.5 moles of copper sulfate, but I don't have that. I've only got 1 mole, so the copper sulfate would run out, leaving some gallium unreacted. And what that also means is that it is this value that you can now use to predict how much gallium sulfate is produced and how much copper is produced, because as soon as the copper sulfate runs out, then the reaction stops and no more will be produced. So when you're working out how many moles of these are produced, you have to use this value here. So the question is, how many moles of copper are produced? Well, if you use the gallium incorrectly, you would predict that 1.5 moles of copper would be produced. But that assumes that all of the gallium is used up, which we know it isn't. So we have to always use our limiting reactant, which is our copper sulfate. And the ratio between the copper sulfate and the copper is 3:3, which simplifies to 1:1, which means if I had 1 mole of copper sulfate, I would produce 1 mole of copper. How many atoms of copper is that? Well, we know that 1 mole is 6 times 10 to the 23 atoms. So there's 2 more questions there. Exact same process. Identify the excess reactant, identify the limiting reactant, and then use that to predict how many moles of a product are formed, and then finally how many molecules or how many atoms does that actually represent.